Intermolecular forces are forces that act between molecules, not within them. They are interesting because they determine the boiling point of substances and how a substance may react with other substances, so they are important. Okay, they are weaker than their counterparts, which are intramolecular forces, which are ionic, metallic, and covalent. Okay, these covalent. Okay, these are intramolecular forces. We are not gonna discuss them. That's not covalent anyway. We're here concerned with intermolecular forces. Okay, let's start with ion-dipole interaction or ion-dipole force. Okay, it's an interaction between an ion and a dipole. A dipole is simply a molecule with two poles, each bearing a different partial charge. They are not bearing complete charges. For example, HCl molecule. Let me grab my pen. HCl. Okay, HCl is a polar molecule. If you do not know what polarity is, consider watching the previous video I made. Okay, Cl bears a partial negative charge and H bears a partial positive charge, so it is a dipole. When it's close to an ion, for example, a sodium ion, which is a cation bearing a positive charge, there would be an electrostatic attraction between this part, between this Cl and this ion. Okay, it's an electrostatic attraction that keeps them closer to each other. Okay, essentially all intermolecular forces are types of electrostatic attraction like this. Okay, that's induced ion-dipole interaction, and it's good to point that in a solution there is no one molecule of HCl, there are many. Okay, this is also an HCl molecule. Always the Cl will be pointing toward the ion, toward the positive ion, and the hydrogen will be pointing away since it will be repelled because it bears a partial positive charge. Okay, this is ion dipole. Let's go now to ion-induced dipole. Okay, it is similar to this, but the only difference being that it is between an ion and a non-polar molecule which becomes polar by induction when it is close to an already charged object. In this case, it is the ion. Okay, for example, let's take again the sodium. When it is close to methylene. Methylene is nonpolar. All hydrocarbons are nonpolar. Okay. The part of this molecule that is close to the sodium ion will get a partial negative charge because this sodium ion will attract electrons from this side. From this side will attract electrons from this side, leaving this side with less electrons, so it will bear a partial positive charge. And because two opposite charges are close to each other, there would be an electrostatic attraction between the two. That's ion-induced dipole interaction. Okay, now let's get to van der Waals interaction, which are interesting here because they have types. Okay. Van der Waals are a group of interactions. They are not only one type of interaction. Okay, it happens between electrically neutral molecules. If you notice here, the ion is not electrically neutral. It bears a positive or a negative complete charge. Whereas the HCl, for example, and the ethylene, they are neutral. However, in HCl, there is polarity. However, it is neutral. Van der Waals is concerned with these neutral molecules. So, Here the molecules have no net positive or negative charges, only partial charges. And the different types of van der Waals depend on where the partial charge is from. Let's start with the simplest one, which is London's dispersion forces. London's dispersion forces. It is present in all molecules, all of them. However, it is the only one that acts in nonpolar molecules. Okay, it is easier to understand it from this animation which I made. Okay, uh, electrons are orbiting the nucleus all the time, and they are most of the time equally arranged around the nucleus. However, let's take some examples here. You can see that electrons are equally distributed. However, here sometimes the electrons might be drawn to one side more than the other side. In this case, this where the electrons are more concentrated will bear a partial negative charge, and this will bear a partial positive charge. So it will have a dipole. Okay, so here is a molecule, a neutral molecule. The electrons might be sometimes, for very short periods of time, more concentrated in one side than the other. So it will have a dipole. It is an induced dipole which induced itself. So another name for it is induced dipole interaction. This interaction is stronger the larger the molecule is. For example, let's draw these hydrocarbons. This one, 1, 2, 3, 4, 5, 6. This hexane will have, for example, more London interaction with other hexane than a butane, with other butanes. So since this is larger, it will interact via London dispersion forces more than this smaller molecule. And these London interaction are important in very large molecules like proteins. All of van der Waals are important in proteins and other large molecules. Let's get to the next van der Waals interaction, which is induced dipole. It should be dipole-induced dipole interaction. Here the dipole induced itself. Now here the nonpolar one will be induced by a dipole. For example, let's take HCl as a dipole. HCl as a dipole with a nonpolar molecule. Let's take ethylene, for example. What's the problem with ethylene? Ethylene. So, as in the case here, the dipole will induce this molecule to get partial positive and partial negative charges to be a dipole, and an electrostatic attraction will happen between them. Now let's get to I forgot to say that here also this one will induce its neighbor. So let's say that this is its neighbor. This side will get a partial negative charge, and this part will get a partial positive charge, and an electrostatic attraction will happen between them. All of them are electrostatic attractions. Let's get to the final van der Waals interaction, which is dipole. This one is the strongest among van der Waals interactions. it happens between dipole and a dipole. For example, HCl with an HCl. I don't want to draw that again and again, so you get the idea. Between partial positive and the partial negative charges of two different dipoles. Okay, one type of dipole-dipole interaction, or one special case in dipole-dipole interaction, is hydrogen bonding. Okay, it is sometimes referred to as a specific entity because it is very strong than those all van der Waals. But here I consider it part of dipole-dipole, which is part of van der Waals interaction. Okay, so know what your doctor or professor wants. Hydrogen bonding is when one dipole has hydrogen attached to a very electronegative small atom. For example, let's take one dipole. For example, let's take H2O. Okay. Hydrogen is attached to a very electronegative atom. Okay, it might be oxygen, fluorine, or nitrogen. Okay, and it interacts with another molecule that has oxygen, nitrogen, or fluorine, not necessarily bonded to hydrogen. For example, let's take CH3F. Okay, CH3F. Okay, the interaction between the hydrogen, which is partially positive, and the fluorine, which is partially negative. Fluorine is more electronegative than carbon. The interaction between them is hydrogen bonding. This is hydrogen bond. Okay, a water molecule can make two hydrogen bonds. Okay, let's draw another like this. H. Okay, this is a hydrogen bond. A hydrogen bond is commonly referred to as drawn as a dotted line. Okay, another one would be like this. Okay, this is how water makes two hydrogen bonds. And the fact that water makes hydrogen bonds give it many characteristics which we are gonna discuss in next videos, not in this one. Here we're only defining what hydrogen bonding is. And the atom, or the electronegative atom, bonded to the hydrogen is called, okay, let me just delete those off. This is annoying. Okay, the one that this one is called the donor, the hydrogen bond donor, since it is donating its hydrogen. It's like donating its hydrogen. And this one is accepting the hydrogen. So this is an acceptor, a hydrogen bond acceptor, and this is a hydrogen bond donor, D. Okay. Hydrogen bonds are essential to keep the two strands of DNA from separation and are essential in many proteins. Let's take here, look at a picture from Wikipedia for two nitrogenous bases, guanine and cysteine. They are bonded by hydrogen bonds between them, and each one is in a different strand of DNA. So you notice here, this is an atom, which is an oxygen, which is electronegative and bears a partial negative charge, and here is a hydrogen bonded to nitrogen, and it bears a partial positive charge. Here is the same, partial positive, partial negative, partial positive, partial negative. Just make sure that the hydrogen is bonded to N, O, or F, and it is close to an N, O, or F, and a hydrogen bond will happen. Just keep in mind that the hydrogen bond is between them. Okay, this is not the hydrogen bond. This is a covalent bond. This is the hydrogen bond. Okay. Our next and final intermolecular attraction would be salt bridges, which I made the last one. Okay, although it is strong. Take it below. Okay. Salt bridges is a combination between ionic attraction and hydrogen bonding. Let's take this. Okay, this image also from Wikipedia. You notice here that this is the salt bridge between glutamic acid and lysine. Okay, this is it. The glutamic acid in body pH, which is around 7, around neutral, the glutamic acid will bear a negative charge on its carboxylic acid group, and the lysine will bear a positive charge on its amino group. So there is an electrostatic attraction between two opposite charges. Also, there is a hydrogen bonding between the NH3 and the C double bond O and the COO minus. So salt bridge is a combination between an ionic attraction and a hydrogen bonding. You will almost only hear it in proteins. So sometimes you read that a salt bridge form or a salt bridge breaks. Well, salt bridges are these types, okay? And glutamic acid and lysine are amino acids found in proteins. They are not commonly found in other substances, as far as I know. Okay, at the end, just several notes. Hydrogen bonding is the strongest among van der Waals interactions, and salt bridges is the strongest among what we discussed here. Then dipole ion-dipole interaction. Okay, remember that hydrogen bonding is the strongest among van der Waals, not among all what we discussed here, because ion-dipole and salt bridges are stronger than it. It's a common mistake. And van der Waals, all of them are accumulative, so in large molecules as proteins. The large number of these weak interactions make them strong enough to stabilize the molecule, as van der Waals forces play an important role in determining the structure and the folding of proteins. At the end of this video, I would like to remind you that there is a PDF file for this video series. Make sure you get it. It's great for reviewing this video and relate it with other videos of this series. You can find the link in the description below. Thank you for watching and good luck in your study.